Okay. I think we're rolling, Michael.
All right. Oops. Well, hello, I'm Michael Ferguson. I work at HPE on the Chapel programming language. Today I'm going to demo some getting started with Chapel kinds of features. So as a starting point, I have Chapel set up so that it's in my path. I did that by, let's see, what did I do? I went to a directory where I have a Chapel checkout and I ran this command, which adds it to your path. There are other ways to do that. You can also install it, but that's what I have going right now. So then we can write a hello world program. I already wrote this little tiny one just to check that things were working before I started today. So it just says write line hello world. That's going to print out hello world when we run it. So we'll compile it with chpl and then hello. And then we run it and it prints out hello. No surprises there. So that's the very starting point of how to compile and run a program. You'll notice that when I compiled it, it created this thing. That's the program you can run. This is the source code for our program. And that's hello. From hello, we can go to configuration constants. I'm going to just remove, no, I don't want to remove hello. Let's make a configuration file. So Chapel has this neat feature where you don't have to do argument parsing. In most other languages, you'd write something like this. You write this is you'd write some kind of loop over your arguments. So here's an example. I'll just show that. We'll compile that. So it did. I just ran it with this name. So the first argument is the name of the program. I can give some other arguments and it finds them in here. So typically you process these arguments. Maybe you'd say something like if arg equals input, then you'd do something or other. But in Chapel, you don't have to do any of that. Say we want to have a program that has an input. We can write config const input, make it a string. Then down here, I don't need my arguments right now, but I could use them if needed. So this makes a variable that's called its const means it can't be modified after it's created, and its config means that it can be set in the command line. So let's compile that program to see what I mean. So that if I run help with it, you can see that I've got a configuration variable called input. If I just run it now, its input is the empty string. I'll make it print it out with quotes around it just so it's clearer what's going on. Oops. So input is the empty string. Why was that? That's because the default value for a string is the empty string. And we could have put a different default here, right? If I compile that now and run it, then instead of empty string, we have that default. But in either case, as I was showing with the help output, we have this variable input, and we can set that when we run our program like so. So the configuration constants are a neat way to avoid even needing to bother with command line processing in simple cases. If you're doing something really complicated, you might well need to use that arguments to main like I showed at the start. I'll show one other thing with configuration constants. We also have we also have other types of variables in Chapel. You can have a const means something that exists at runtime when your program is running. It won't be modified after it's created. A param exists within the compiler. So I've got this config param setting, and this is an integer 0, so this variable is inferred to have the type integer. Okay, so what's this do? If I compile configuration again, I run it, then you can see that I got the default value of setting, which I set right here. But and if I run help, I don't see it in this config vars section because it's a compile time option because it's a param. So to set that, we would use the compiler, use the set flag on the compiler. So here I'm setting it to 23 at compile time because it's a compile time value. One interesting thing about config params is that they can change the type. So this config param, I initialized it with 0. If we had the if we have the command line setting it to something else, like we'll say 1.75. This is now a floating point number. It's not an integer, so it has a different type. But all the code that I had here, it was just printing it out and it was inferring the type here. So you can, if you want to, sometimes it's helpful to make config params that where you can change their type when you're setting them on the command line. All right, that covers configuration constants and configuration parameters. Next, let's talk about how to write a function. I actually showed a function earlier when I was talking about main. But we'll do it a little more slowly for functions. So we already saw you can make a variable like this. This is a variable, we say it's at module scope. It's kind of like a global variable. You can also make a function. You make a function by putting proc and then the function name. You can add the parentheses. It's also possible to have functions without parentheses. Usually you would want parentheses. And then you put what we'd call the function's formal arguments. So I'll make a function that adds 2 integers. We'll add 1 and 2, and hopefully we'll get 3, right? So here's a call to our function. This is pretty similar notation to most languages. The main things to know about Chapel if you're coming from another language is functions start with proc. Types are specified after the variable with or formal that they're talking about with colon. Right? Whereas if I was writing this in C, this would be oh, I've got this error. Here, another element is that I didn't put the return type. It's inferred, but we can put it here. And then I compared with C. Note that is usually 32 bits. In C, in the integer type isn't strictly defined by C. It might depend on your compiler's configuration. In Chapel, int is always 64 bits, If you want a 32-bit int, you'd write int 32. Okay, anyway, let's run this program now that we've talked a little bit about functions. So we'll compile it, and we'll run it. And we have computed that 1 plus 2 is 3 in a function. So functions can be really important to put your program into groups of code that can be reused in different places. So that was a simple function. Let's go to how to write a loop. Well, the typical case is you write something like this. So I'm just printing out I in here so we can see what happens in our loop. So this will just loop over, start at 1, end at 10, including 10, and print it out. Let's try it out. So here I'm just compiling it, and then if the compile command succeeded, going on to run the program that I just compiled. Right, so that just printed out all the numbers 1 through 10. What if I wanted to write a loop that starts on 0 and iterates 10 times? Then I would write it like that. This says start at 0, continue, but until you reach 10, but don't include 10. Don't run this right line for 10. So we'll run that one now. So it should print out 0 through 9. Okay, so that's a simple for loop. We can also write a while loop. So I'm going to put curly braces in here so we can have the same variable. This just introduces scope like in some other languages. Okay, so yeah, I've got a variable I. It starts at 0. So I could write this same loop like this. Right, so the above loop here is the same as this while loop down here. Occasionally, one needs to write a while loop because there's some other sort of way that we need to exit the loop. We can exit a loop from here early if we want to. We can say if I equals 5, then break. We can skip something. Let's have it skip 1. We can continue. Continue means go on to the next iteration of the loop. So if it's I is 1, we continue, then it'll go on to iteration 2. Then we'll print out, and then if I was 5, after we print out 5, we'll break. I'll comment out this stuff down here for now. Let's just see what that one does. So I'm expecting it'll print out 0. It won't print out 1 because it'll continue to 2. So it prints out 0, 2. And then when it gets to 5, it'll print out 5, and then it'll hit this, and it'll stop printing entirely. Let's see if that does, in fact, what I expected. There you go. It started at 0, didn't print 1 because we told it not to with that continue, and then when it got to 5, it stopped. So you can use these same continue and break kind of things in while loops. There's also do while loops. But most of the time in Chapel, we're going to be using variants on the for loop. So let's talk about variants on the for loop. So one thing is occasionally you have a need to iterate over 2 different things at the same time. So to talk about that, I'm going to make 2 arrays. I've got 10 things in array A, and I'm going to have 10 things in array B. Oh. And then I'm going to iterate over both of those arrays together. First of all, let's initialize these arrays to something. I'll initialize array A to I'm going to initialize it in a different way. So you can initialize these with loop expressions, but I don't want to tell you about loop expressions yet. We'll get there later. So let's initialize these with a loop. These are going to be initialized to 0 right when they start, but we can change their values to something else. See, I'm trying to, I was trying to show you, I was trying to show you something with these two arrays, but I realized that I need to show it to you to do this initialization. So I'll just do one array. So say I want to initialize, sorry, let me getting ahead of myself. If I wanted to initialize them all to 1, right, I could write this loop because we can iterate over the array. The for loop doesn't have to iterate over a range like we were showing here. It can iterate over the array and go do something for every element in the array. And it just sets all of them to 1. So let's just run that just to see that it works. So here we are. This is the code we're about to run, and then it printed out. We compiled it and ran it, and it printed out a bunch of 1s because we initialized every element to 1. What if we wanted to do something more complicated? Like what if we want to initialize this to the index times the index? Well, what we'd usually do is we'd use a zippered iteration. For an array, in Chapel, the domain of the array is the index set for the array. So in other words, for this array, the domain is 0 through 9. So if we use zippered iteration, we put the zip keyword and we say what things we want to iterate together. And then we put a tuple syntax with the parentheses here to say what to call those values that we're iterating together. So element will be the iteration variable for A, and I will be the iteration variable for A's domain. So let's just print this out. So I'm not changing any of the elements, so they're all going to be 0. And we're going to see I count up starting from 0. I'm going to go ahead and delete this stuff so we can see our program more easily. So here's the program we're running, and then here's the output from it. So the element never changed because it started out at 0 when it got initialized here when we created the array, and we never set it, so it just stayed 0 forever. The I value is going from 0 to 9 because that's what this range is, and that's the indices of the that are in the arrays domain. So we can set. I was saying maybe we want to set the element to the square of the index. So we can do it like so. We'll run that, and we should get a printout of the first 10 squares if you start at 0. So that's a little bit about zippered iteration. So that was cool. I've covered in the last little bit, I've talked a little bit about how you write an array, and I've talked a little bit about zippered loops. You can write multi-dimensional arrays. You can write other arrays that operate on the same domain. I'm thinking about which of those I want to show you. I think what I want to show you next is a for all loop. So Chapel has a way to make Let's see, let's change this to something we can measure. So I've got config const. In Chapel, you can just put on your any integers you want. You can put underscores just as separators for your own reading. So I'm going to make my array go. So I've got an array of 100 million integers, and I'm going to set it to I squared. Okay. So I'm going to start out with a for loop, and I'm going to time how long it takes to do that. If we're going to time something, we need to add the fast flag to the compilation. That will enable optimization. So here's the program we're running. I forgot to time it. Oops. So that took this long. Looks like I'm going to need a bigger array for this to be fun. Change it to a bigger array. There's a nice pause. So it took almost a second to initialize my 1 billion elements. Now, if I change this to a for all, and I do this same thing, put the time here, then this will become a parallel loop, and it looks like it took the same amount of time. Oh well. Must be that this wasn't the initializing that wasn't the slow part. Anyway, this was so that made this thing into a parallel loop. I don't know why it didn't go faster, but that's okay. Sometimes you know, you parallelize something and it runs into a different bottleneck. This being a parallel loop, we can run the iterations of this on many cores at once. The for all loop says go ahead and run that in parallel according to whatever the first thing your zippering wants to parallelize it with. So in this case, we're asking the array to make it parallel, and then we the body of the loop is going to run. And this loop that was fine because these iterations aren't impacting each other. If I had a loop that was like something like this, I had a loop that was something like this. You know, then if you think about what these iterations are doing, they are going to depend on each other. So this loop is going to have race conditions because they can be run in any order. And them being able to be run in any order is what, as the programmer, we convey to the Chapel compiler when we use the for all keyword. Okay. The loops. So I want to cover the loop expression. So I can write a loop expression. I can write this whole thing. Remember that I had this thing here, right? So that thing, instead of initializing the array to 0 and then setting each element to the square of the index, I can start out the array by initializing it to the square of the elements. Let's try that. And this is called a loop expression. So oftentimes you have a loop and then you put statements inside of it. This is inside of this initialization from the equality assignment symbol here. and then it's going to contain what to initialize each element to. Let's try doing that and see what happens. Well, that's interesting. That got a lot significantly faster because now the computer's only initializing our 1 billion elements once instead of initializing them to 0 and then replacing them with I squared. I would presume that if I put a for loop here, it will be slower. And find out. So we can have loop expressions that are those regular serial loops or parallel loops. And indeed, yep, it was slower without the parallel loop. There's another way to write this, which is with this, which is sort of a shorthand form of the it's a shorthand form of for all. It's the same as if I had written that. And that should behave just like the for all case did. Oh, except I don't put the do in that case. Okay. So this one, the performance of it is similar to the for all loop because it does the same thing. There are some minor differences between those two forms, but mostly this one is just a shorthand. All right, well, here I think I've covered the things I had in mind. We started with configuration constants and parameters. We talked about writing a simple function. I showed writing a couple of loops. We did show a couple of array declarations. I didn't show a multi-dimensional array yet. I could do that. And I can show so I can show two arrays over the same domain. So let's do that, and then I'll ask if anybody has any ideas for something they want to see next. So this I'm making a 4x4 two-dimensional array of integers. Here, let's make this one be real numbers. So so here's the program we're compiling. Then we compiled it and ran it, and it printed it out. It printed out a two-dimensional array. So it just puts new lines between the rows. I could do something like set element. Let's set all the diagonal elements to 1. There's only 4 of them, so making a parallel loop isn't going to be useful, but I think it's fun to write parallel loops when you can. Okay, so we're setting all of the diagonal elements to 1 because, oops, I have to put I comma I. So I comma I will be the diagonal elements and set them all into one with a parallel loop because there's nothing about this loop body that depends on other iterations. Each one can be done at the same time or in any order. So there we go. So this one is 0, 0. This one is 3, 3. Just to show that, I'm going to change this to set it to I. So there's 0, 0. There's 3, 3. So that's some two-dimensional arrays. The next thing I'm going to show is what if I wanted to make a second array that worked. If I wanted to make a second array that worked with the same shape. You can write it a couple of ways. You could write this Maybe I want to have an array of integers that has the same shape as this thing. This says that the shape is the domain from that one. If I wanted to have one that was exactly the same elements, I can initialize it, copying it. If I wanted to have one that was, let's see, let's call this same elements. I want to have one that's same shape, different elements. We'll just call it same shape. And you can say, you can declare it like this. So this just says the type of this thing is going to be the same as that type. And the type is everything after the colon. So that included the shape and the element type. Or we could have one that has the same shape with the different elements here. So those are some patterns with arrays. One more thing you can do is you can declare the domain separately. So we have domain literals are these things with curly braces. They're curly braces because they're referring to an index set. And that's a common notation in math for curly braces for sets. So I can make an array over that domain that stores one thing. I can make another array over that domain that stores another thing. And then later on, if I wanted to, I can change this domain to be something else. So let's say we'll change it to 0 to 1. And this will cause arrays A and B to be resized. Let me go ahead and delete those things and we'll run this thing. I'm going to set the diagonal elements again. So I set the diagonal elements so that we have something we can look at. And then I'm going to print these out. And I'm going to print out that I'm resizing the arrays, and then we'll print out these again. And then we'll compile and run that, and we'll see what it does. So here we made 2 arrays. They're going to be 0, 1, 2, and 3 in each dimension. They're 2-dimensional arrays. One of them's integers, one of them's reals. So here's the A array. They're all integers, and I initialize the diagonal. Here's the B array. They're all reals or floating point numbers, and I initialize the diagonal. And then when we resize the arrays, we got a little 2x2 array at the end, and it kept the elements that existed in the original array. So that's a little bit about some of the more odd things you can do with arrays in Chapel. All right, any requests for something to see?
Sure. Michael, can you tell us a little bit more about loop control and using begin and co-begin within loops?
You wanted, I can talk about begin and co-begin. I don't think about them usually as relating to loops. So begin is a way you can create a task, and co-begin is a way you can create 2 tasks. So call it task 0. I'll just make these print out because I don't have anything more complicated to implement right now. So I'm just making little functions that are notionally what our computation would be doing. So what's going to happen is, and I'll go ahead and put this all in a function just so we have maybe a, I don't know, maybe depending on who you are, maybe it'll help things be clearer. Okay, so when program starts, it's going to run main. It's running main, and right here it hits this begin statement that says go create this task and then forget about it. So it will create this task, and when it gets around to it, it will run this. But that might happen after these other things. So like here, I'll put a write line in between or after begin before co-begin. Okay, and then this one, this is a co-begin. This is going to say create these two tasks and have them run at the same, they're not required to run at the same time exactly, but they both have to exist as tasks. So it will create both of those tasks together and then wait for them to finish. So if we run this, I'm going to just print it out and then, so I'm just printing it out, putting a new line so we can see the difference, compiling it, and then if that is succeeded, running it. So here's the program we're running again. And you can see that task 0 happened after everything else because this task is called, we call that sometimes a fire and forget task. We said begin, we didn't say when it should do it, and we didn't wait for it to happen. So it will kind of happen when the implementation gets around to it. The co-begin, these two ran together and then it waited for them to finish. And at the end of the program, it waits for all of those fire and forget tasks. So if I run this a few times, you can see some different orderings we can get. And it's even possible for us to get task 0 to run before this printout, but it doesn't look like the implementation is doing that right now. Anyway, that's a little bit about begin. There's also co-for-all versus for-all. Bonnie, is that something you'd like to talk about too?
Yeah, absolutely. It's just nice to
Okay.
see your short demo. Thanks.
Okay, so co-for-all versus for-all. So we saw begin and co-begin. We also have co-for-all and I already showed for-all. So I'm not sure what I would put here that would behave differently, but the implementation of like what's kind of happening inside of it is very different. So we'll just make some, just so it's valid code, I'll write my, config constant, and then we'll loop over from 0 to n. Okay, so how are these different? This one creates a task for each of the iterations. You might want to do that if you had a situation where those iterations were going to use synchronization constructs to wait for each other or do barriers or something like that. This one creates a number of tasks that is not set by you, the programmer. You're saying when you use this construct, it doesn't matter to me how many tasks you create. You go do something that seems intelligent. That means that in typical practice, when you're running on a multi-core CPU, this will create one task per core and then divide up this range among those tasks. Whereas this one creates one task per iteration. So this one creates 100 tasks, and then this one creates number of cores. Tasks according to the number of cores. So generally speaking, I recommend using for all. One common situation where we don't want to use for all is when you're writing something in distributed memory. Like this pattern, right? So this, the locales array, which starts with a capital L. The locales array indicates which distributed memory nodes you're running on. With this pattern, we go on each node and create a separate task on each node. If we said the same thing with for all, so let's see, this says create a separate task on each node or locale. This thing says create number of cores tasks and then run. And this is something at some point maybe we'll change the behavior of this loop, but that's what it does today. This will say, look at where you're running at the start of your program, which is on a single node. It will say how many cores are on that node. Okay, I'm going to create that many tasks to run this, and then it will go on to those different other locales in sequence. So say you had 4 cores. If you had say you had 4 cores and 16 locales, right? Then what this would do is task 0 would run on locale 0, 1, 2, and 3 in sequentially. And then task 1 would go on locales 4, 5, 6, and 7, and sort of so on, right? So the issue is that this doesn't actually create the parallelism across the system because it's limited by the number of tasks on one of the nodes, when what you'd want to do is create tasks for each node. I did not talk in our other things I've been demoing. I've not been talking much about the distributed memory features of Chapel, but this is one case where the for all loop is usually more appropriate than a for all loop, which is what we were talking about here. All right, any more questions?
I have a quick question.
Sure.
So if I have like multiple nested for all loops, does that just like saturate the tasks on the system, or is there like some compiler optimization that, just turns the most inner for all into a for?
Yes, let's talk about it. So you might have something like, I just like to make things as concrete as possible so everyone knows what we're talking about. So this is the kind of thing you're talking about. So the nested means I've got this loop, and then contained in its loop body, I've got another loop.
Mm-hmm.
And then do something. So what happens is the implementation will run this. It will create number of cores tasks to run this thing, right? And then
Yes.
inside of here, it will say how many tasks should I use when I'm running this for all loop? And to answer that question, it will look at how many tasks are currently doing something. Since they're all already doing something running this thing, it will just run them in non-parallel.
Okay.
If you had I mean, I had a big N, right? If this was like, if I had like, 3 or something here, right? Then I would expect to get some parallelism out of this thing. So I think this kind of thing it can be okay. Sometimes it adds overhead. Like if you've got a tiny amount of work in this loop and this outer loop is happening a lot, it can add some overhead to even do that check to see how many tasks are we running as
Okay.
compared to writing a for loop in here.
Mhm.
But the implementation does try to make it so that writing this is allowed and can be okay. But it depends on the specific case. Like if you're thinking about optimizing it or something, it depends on the specific case whether or not it will go well, because there is some overhead to, like if it's always going to find out that there's nothing to do here in parallel, there's some overhead to computing that.
Okay. Thank you.
Yeah.
Is it similar for each? Like if I have multiple nested for each, will that ruin my performance or?
Are you talking about running on GPU?
I was no, just for CPU, but in the end, I am curious about how it would work on the GPU.
Okay, so I can answer the question on the CPU. For the GPU, I'm not so sure exactly what the situation would be here.
Okay.
On the CPU, these for each loops, which I have not talked about yet, and apparently my Vim is not configured to syntax highlight. It is a keyword. These for each loops say, I'm writing a loop that can be run in any order, but I don't want you to create tasks to do it.
Yeah.
That means that it's going to run in any order using other features of the hardware. For example, it might use, if you're running on a GPU, it might use those sort of SIMT processing on the GPU. In
Mhm.
GPU terminology, those are called threads, but that's very confusing with what CPU threads are. So I will just call it SIMT for now. On the CPU, it would be use vectorization. So by writing it this way, you're encouraging the compiler to vectorize these loops. And
Yeah.
on the CPU, it will pick the inner loop to vectorize, and it won't vectorize the outer loop. Is generally what will happen.
Okay.
We can there are some cases where it might do something else. And we have some ongoing work to look at outer loop vectorization on the CPU. But generally speaking, I would expect it would be, number one, it would be harmless on the CPU, and that only the inner loop will be vectorized.
Okay. Okay. Are is it better to if I'm writing code that is going to be on CPU and GPU or should be like agnostic,
Mhm.
would it be a safer bet to write everything as a for all loop? Um, just I don't know. Do you see what I'm saying? Like, because they're sort of equivalent on the GPU, but if I'm unsure, should I use for all or for each?
The place that I would use for each is if it was something that was small enough that I was worried about the overhead of creating a bunch of tasks to do it.
Okay.
Right. So if I had something like this, right? Right? Like here, there's no harm in putting a for each here as opposed to a for if I know that my loop can be run in a way that I don't care what order the iterations run,
Yeah.
right? In contrast, if I've got 10,000 elements, I wouldn't be worried about the task creation overhead here. I'd say, well, there's going to be a lot of stuff happening in this loop, so having a little bit more overhead isn't a big deal.
Okay.
So I would generally be I would be trying to write big loops and use for all. And then if that's not working, there are some cases where you'll need for each or plain old for if the for all loop is like the loop's too small and the for all is adding overhead. But those are all things you need to measure in your program in order to answer. So like if you're just starting, and I'd say, well, start with that, and then you can start to measure things and see what's going quickly and what's not as fast as you hoped.
Okay. Thank you.
Sure. Right.
And
Well,
just
thank
a
you.
quick question to clarify. You said for each is going to basically implement those tasks in any order, but for will implement them one by one in the order that
That's
they're
right.
listed. Okay, just want to
So
clarify that.
it, like earlier, I was showing something like, I had
Yeah.
an array,
Got it.
like this
On it in
thing.
a specific
Yeah,
order.
you need to put that in a for loop. Otherwise, you'll basically be lying to the compiler, right? If you write for
Yeah.
each here, then this
knows?
you'll be
Yeah,
creating a race
okay.
condition. Who knows what you'll get?
Mhm.
Same with for all. Same with co for all, actually, right? Because that'll
Got
just
it,
create a
got it.
task per thing. Here I have it set to create 10,000 tasks. That's probably not a good idea. Probably slow, but beyond that, it's
Mhm.
race conditions.
Okay.
So yeah, for something like
makes
this, you'd
perfect
write it like here. One of the things about changing some code, if you have some code that looks like this and you want it to be parallel, what you'll be looking for is ways to change this operation into something that can be done in parallel. And oftentimes the way that that works out is by using more than one array. Right, so like
Got
if
it.
this was my loop, I mean, this is a little bit silly, right? Because I'm just shifting all the elements in the array one. So, I could just make the next part of the code use I plus 1 or something, right? But assuming it was doing something more complicated, what you could do what you can do to make it parallel without any race conditions is, and I'm going to go ahead and declare a just the usual kind of thing here. So you can a separate array and store part of the computation. So what you can do is can make B, and I can say something like this. Right, so now this is fine because the sort of the input to each of these loop iterations is not being changed by anybody. And the output to the loop iterations is based on index variable in a way that it is unique. So there's not going to be any race conditions or collisions where different tasks are writing to the same memory, right? So now I've just got the result of doing all of that. I've just got it in a different array now, right? So that kind of trick can help make something run in parallel that maybe at first it didn't look like it could. But of course, it depends on what you're doing, whether or not it's reasonable. And if you're trying to write something in parallel, it's always good to try to understand if you're implementing something well known, is there like a parallel version of it that you can look up for like generally what you should be doing in your program.
That's great. Thank you for that explanation.
All right, cool. Well, any other questions? We have 4 minutes left in our scheduled time here.
That was great, Michael. Thank you.
Yeah. Thank you. Yes. Thank you
All
very
right,
much.
good. We'll conclude. I will write the goodbye for now program to conclude. Just for fun.
Oh. Oh.
So long for now. And we'll print that out because it's like the opposite of hello world, right?
Yes. Goodbye, sweet
So
world.
there you go. So long for now. Thanks, everybody.
Thanks, Michael.
Talk to you another time.
Bye.